Regularization is one of those major fields of research within machine learning. There are many published techniques, and I guarantee you, as soon as you watch this, there's many more out there in scientific journals for you to see. We've already mentioned early stopping. There's also dataset augmentations, noise robustness, sparse representations. They're all groups of methods under the umbrella of parameterized norm penalties, and many, many more. In this module, we'll have a closer look at L1 and L2 regularization methods from the parameter norm penalties group of techniques. I like to penalize in the complex models. But before we do that, let's quickly remind ourselves what problem regularization is trying to solve for us. Regularization refers to any technique that helps generalize a model. A generalized model performs well not just on your training data, but also on never before seen test data. Let's take a look at L1 and L2 regularizers. L2 regularization adds a sum of the squared parameter weights term to the loss function. This is great at keeping weights small, having stability, and a unique solution. But it can leave the model unnecessarily large and complex, since all of the features may still remain, albeit with a small weight. L1 regularization, on the other hand, adds the sum of the absolute value of the parameter's weights to the loss function, which tends to force the weights of not very predictive features, useless features, to 0. This acts as a built-in feature selector by killing off those bad features and leaving only the strongest in the model. The resulting sparse model has many benefits. First, with fewer coefficients to store and load, there's a reduction in storage and memory needed with a much smaller model size. Seems like an awesome win. This becomes especially important for those embedded models, like on the edge on your phone. Also, with fewer features, there are a lot fewer multi-adds, which not only leads to increased training speed, but much more importantly, increased prediction speed. Even if you had an amazingly accurate model, if a user is waiting 60 seconds or a minute and they expected it to be sub-second, it's not going to be any use. To counteract overfitting, we often do both regularization and early stopping. For regularization, model complexity increases with large weights. And so as we tune and start to get larger and larger weights for rarer and rarer scenarios, we end up increasing the loss, so we stop. L2 regularization will keep the weight values smaller, and L1 regularization will make the model sparser by dropping out those poor features. To find the optional L1 and L2 hyperparameters during your hyperparameter tuning, you're searching for a point in the validation loss function where you obtain the lowest value. At that point, any less regularization increases your variance, starts overfitting, and hurts your generalization. Any more regularization increases your bias, starts underfitting, and hurts your generalization. Early stopping stops training when overfitting begins. As you train your model, you should evaluate your model on your validation step every so often, every epoch, a certain number of steps or minutes, etc. As training continues, both the training error and the validation error should both be decreasing, but at some point, the validation error might actually begin to start increasing. It's directly at this point that the model is beginning to memorize the training dataset and lose its ability to generalize on the validation dataset. And more importantly, forget the validation dataset, it can't generalize to what you're going to be predicting on in the future when you deploy this model out in the real world. Using early stopping would stop the model at this point, and then would back up and use the weights from the previous step before it hit this validation error inflection point. Here, the loss is just length WD with no regularization term. Increasingly, it's interesting that the early stopping is an approximate equivalent of the L2 regularization, as is often used in its place because it's computationally cheaper. Fortunately, in practice, we always use both explicit regularization, L1 and L2, and also some amount of early stopping regularization. Even though L2 regularization and early stopping seem a bit redundant, in real-world systems, you may not quite choose the optimal hyperparameters until you get your model out there in the real world and see what a real world data set can do for it.